Oh yeah. You guys feeling that? That's some geometry heading your way. You ready to have some fun? All right. Here we go. We're going to be talking about some segments, rays, parallel lines, and planes. And you might know what all these things are, but we're going to get a little bit more specific with them in geometry. So let us start off with the definition of a segment. Now, in the first two videos, in 1-3, we talked about some undefined terms like point, line, and plane. They were kind of like imaginative things because they really didn't have, like a finite length to them. A point didn't have length or width. It almost didn't exist, but yet it's there. So it's kind of make believe, if you will. And lines went on forever. You could never fully draw a line. And a plane was like the biggest piece of paper you've ever seen. Now we're going to talk about some defined terms, some things that are finite, if you will. And a segment is one thing that is finite because you can measure a segment. Okay? If you wanted to draw a segment, you could draw it and be done with it in 2 seconds. And you wouldn't have to spend your whole life drawing it like a line. So the definition of a segment is that it is part of a line with two endpoints. It has length you can measure. It is finite. And the endpoints are the beginning and the ending points. Okay? So, for example, what's it look like? Here's an example of what a segment looks like. And here are two endpoints, Y and R in this case. I could have used A and B. I could have used, who cares, two different letters. They have to be capital because they represent points that are on the segment. Keep in mind that there are, and this is kind of a weird thing here, there are technically infinitely many points on any segment because in between any 2 points, you could always do a point in between that, and in between those 2 points, you could put a point in between that, and then you could get a microscope and see that there's still a little bit of space in between there and go in between that, and it's just a little hard to fathom. And I can't really erase that because I'm going to erase my segment. Okay, so where am I going here? Where am I going, Mr. G? I don't even know. Let's run back here. Here we go. How do I write it mathematically? Now, it's going to look very similar to a line. You can write the 2 points here, forwards or backwards, doesn't matter, YR or RY, and instead of putting a little baby line above the two letters, we're going to put a little baby segment. Now, the thing is, you're not going to put little endpoints on the ends of those little baby segments because sometimes you might get really in a rush to do it, and maybe you put it real quick and real quick, and now all of a sudden, instead of it looking like a segment, it looks more like a line maybe. So you just draw a little line up there, a little segment, if you will, and that's it. You don't put anything on the ends, and that represents a segment. Again, you can go forwards or backwards, it doesn't really matter, but only two letters. Okay? So, first example, name 6 unique segments on this line. Okay, 6 unique segments. What I mean by unique is if I said segment AB, that segment BA is technically the same thing as AB, so it's not unique. So I can't use that as a second example here. So AB is one of them, and you could always just pick 2 points that are side by side, like BC and CD, but again, just like a line, you can skip over letters if you like. For example, we could say segment AC, and that would describe this particular segment right here, ignoring everything else. Some of you might have noticed, well, this is really a line, but there are infinitely many segments on a line. I just want you to name 6 of them if you can. So we could do, BD. We could skip over the C and talk about this segment right here. We could go the longest segment we can possibly do here, AD, skip over A and or B and C, sorry. Then we can just do our smaller ones. We could say BC, we could say CD, and there's 6, and I don't think there's really any others we could do here. The only letter you could not use would be the M. Remember that lowercase cursive-y looking M only is for the line. We could call this line M, and that would be it. Okay, so there are your 6 unique segments on that line. There are 6 and only 6 in this particular case. A ray. A ray has one endpoint and extends infinitely in the other direction. So it's kind of like half of it is a defined thing and the other half of it is an undefined thing. Okay, it's almost like if a segment and a line got together and had a baby, the baby would be, they'd call it ray. So what does a ray look like? A lot of you probably know what this looks like. One end has a definite end, and the other end, well, it kind of looks like a line. Okay, if you were to look at part of it, you'd go, hey, this is looking like a segment. And if you look at the other half of it, you'd go, hey, this looks like a line. But in the end, it's kind of a half segment, half line type thing here. Okay, but keep in mind, this keeps going on and on and on forever and ever in this particular direction. How do we write it mathematically? Now here's where it gets a little bit different compared to a line and a segment. When naming a ray, the end point must be the first point, so you could not name this ray ray HG. So we're going to use a little baby ray, and here is an important thing to note here about baby ray. Baby ray, that's like barbecue sauce. You guys like barbecue sauce? That's delicious. This little symbol up here, okay? Now I'm not drawing another little ray here. I'm pointing to this particular symbol with this arrow, not to confuse you. But it's always pointing to the right. When you write mathematically a ray, you're never going to write the little baby ray up above pointing to the left, okay? It's just always to the right. It's just the way that it is, okay? It's always to the right. Sorry, lefty people out there, you get shunned again. It's always to the right. Now, out of these 2 points, really G is our end point, okay? There's nothing going beyond G, so it's got to be the first letter when you name it. Now, the H here, notice our ray doesn't stop at H, but it goes to H and beyond. So this is kind of like the Buzz Lightyear, if you will. It's like going to infinity and beyond. So that second letter is where it continues to go beyond. So again, you couldn't call this ray HG because H isn't where it definitely stops. And there goes nothing beyond G. So again, that would be an incorrect way of naming that particular ray. So name this ray 4 different ways, okay, 4 unique ways. Now, I could start with my Z up here and say ZV might be one way, ZV, and that's naming this particular ray, okay? Now, here's the thing. What if I said ZC? Is that a different way of naming a different ray? Are these 2 rays here unique? And the quick answer would be, see, I lied. I said quick, but it really wasn't quick. The slow answer would be no, these are really the same ray. We're saying start at Z and go to V and beyond. So that's that ray. And then if I said ZC, I'm saying start at Z and go to C and beyond. So it's really describing the same ray, okay? So those aren't really different rays. So I couldn't say ZC, and I couldn't say ZX either, because that's saying start at Z and go to X and beyond, and that's the same ray. So that won't work either. So now you might be asking, well, what else is there? Well, I don't have to start at Z. I could say, you know what? Let's start at X instead. So I could say XC. And that says start at X and go towards C and beyond. And that would be that ray, which is technically different because we've chopped off that little Z part back there. But again, I couldn't say XV because that would be the same ray. So now that I've exhausted all those, then we say, all right, let's keep going up the line here. Well, I could start with C, and I could say CV. That says start at C and go towards V and beyond. That works. But then I'm kind of out of options here, right? Even if I said, all right, well, let's stop C, and what if I just said V, ray V there? I need 2 letters for a ray. I need a kind of a beginning point and a go towards this point and beyond. There aren't any other points along the ray here. So this is kind of a trick question. You can't name a ray with 1 point. There are really only 3 different ways you could name rays, unique rays, in this example. Now this is just something very small. You probably won't be tested on this, but I throw it in here. But if you have 2 rays that are back to back, and not only that, but they are collinear rays, meaning that they are back to back and they make a line. So opposite rays, so here's one ray, okay, starts here and goes to the left. And then we also have a second ray that starts here and goes to the right, that if you have those back to back, they are always going to create a line, okay? Something just for you to see. Now, what if we got rid of, the term collinear? Would it still make a line? And you might think, well, sure, why wouldn't it? Why wouldn't it make a line? Well, think about the hands on a clock, if you will. The hands on a clock are like rays, if you think about it. We could have one ray pointing up, let's say the 12, and we could have another ray, let's say the hour hand pointing at 3, and they both use the same endpoint right here at the middle of the clock. These are technically um, opposite rays. They have the same endpoint, but technically not because they don't make a line, okay? They're just going in different directions. They create an angle that's not 180 degrees, okay? So not every pair of opposite rays will make a line, okay? And well, that really goes against the whole definition of opposite rays. So they always have to look like this. Now let's go back to the ice cube from the last video. Okay, we talked about there are kind of like 6 sides, if you will, 6 planes that we can see here. The top, bottom, front, back, left, right. And I've highlighted 3 lines in this ice cube. And I'm asking, what do these 3 lines have in common? EA, FB, and HG. And I just pointed out here that they don't intersect, they don't touch. Now, I always have one student that's like, well, technically they do cross, right? Like if this line here were to keep going up, oh man, look at crossed HG right there. They do touch. But here's what you have to think about, that technically this is supposed to be a 3D representation. This line is in the front part of the ice cube. This line is in the back part of the ice cube. Technically, they will not touch each other. Okay, so those 3 lines have no lines of intersection. Oh, I did it again. Okay. But there is something different about these 3 lines. And you might say, well, all 3 of those lines are parallel. They don't touch each other. True, but back in, what do you call it, middle school, I had junior high back in the day. I only had 7th and 8th in the same building instead of 6, 7, and 8. Anyway, there is something different about these. And your math teachers didn't quite give you the full definition of what parallel lines meant. Okay, parallel lines have to be coplanar. Okay, so now which 2 lines up here are coplanar? Which 2 lines are in the same plane? Well, these 2 lines, EA and FB, they're in the same plane. So technically we could call these 2 lines parallel because they are coplanar. Now EA and HG, even though they don't intersect, they're not in the same plane. They are non-coplanar. So what kind of term do we call non-coplanar lines that don't intersect? That is a new word. So real quick here, what's different about them? AE and BF, again, they are coplanar, but AE or BF together, they are not coplanar with line HG. Okay, so we have some coplanar lines and we have some non-coplanar lines. But the thing they all have in common is they don't run into each other. They don't intersect. So now we're going to have parallel lines, which must be coplanar, and this is going to be the big difference here. Parallel lines are coplanar lines that do not intersect. And now we have this new term, skew. Skew lines are non-coplanar lines that do not intersect. So in this example here, I've got, name a line that is parallel to AB. Well, here's AB down here. So to be parallel to AB, it's got to be in the same plane. Well, AB is kind of sharing between 2 planes, the front plane and the bottom plane down here. So there's really 2 answers I could give. I could say EF, that's a possibility, right? They're both in the front here. So I could say EF, or I could say DC back here, because both of those would be in the bottom plane. So I could say EF, line EF is parallel to AB, or CD is parallel to AB. Now here's the thing, there's a third example of a parallel line that's parallel to AB. And I don't know if maybe some of you have seen this yet, or realized this is what's going to happen. But I mentioned earlier There's 6 planes you can see here, but there's really infinitely many planes going on. They're just showing us 6. Well, let me show you a 7th plane that maybe you haven't considered. There's kind of a diagonal plane, if you will, that kind of slices the ice cube here. So technically, we could call this a plane, AHGB. Okay, all 4 of those points exist in the same plane. It just happens to be slicing through the ice cube. So we could name HG a parallel line to AB. That does work. Now, are there any other examples that we could give in this problem that are parallel to AB? No, there are not. If we created other points, then we certainly could. Maybe if we created another point here and called it, what we at, I, and maybe over here, J, and then we could say, hey, maybe IJ is parallel to AB. But we're not going to be in the business of creating additional points. We're really only going to go with what's given to us in this picture. So skew lines to AB. Okay, now here's the thing. There's only going to be 3 situations: parallel lines, skew lines, or neither. Okay, lines that will intersect into each other. So you can think of it this way. EF, we already said, was parallel to AB. CD was parallel, and we said HG was parallel. All right. Now, other lines that run into AB. Well, EA runs into AB at A, FB runs into AB at B, CB runs into AB at B, DA runs into AB at A. Is there any other line that runs into AB? No. Now here's the thing. Whatever's left over that we haven't discussed are our skew lines. Okay? So let's look here. EH up here. Notice, it is not coplanar with AB. It is not in the same plane. And, this one's more of a horizontal in the bottom level, and this one's kind of more of a forwards and backwards type of line in the top plane. Those 2 lines are not going to touch each other, yet they are not in the same plane. So that is an example of a skew line. We could also say FG, same thing. We could say DH in the back here, HD, and GC. All 4 of those lines there, and let's write them all out here. EH, line EH, what do we say? HD, FG, and GC. All 4 of those, again, don't touch AB, and they're not in the same plane as AB, so they must be skew to AB. Okay? And there's always a nice pattern. You can kind of tell that these both make kind of like a 7 pattern here, and that is kind of a common thing that you will see in these cube type pictures here with a particular line like AB. So let's try some more here. So name 3 sets of parallel lines, and can you do it without repeating a line? Okay. What I mean by that is if I said PT, line PT, and here's the symbol. Maybe you guys have seen this before. The parallel symbol kind of looks like an 11, if you will, or 2 L's right next to each other. So I can say PT right here is parallel to, and I'm just going to say RU. RU what? Nothing. I meant line RU. I'm sorry. I didn't say line RU. So those 2 are coplanar. They're in the front plane here, and they will not intersect each other. Now, what I mean by without repeating a line is now that I've used PT and RU, I can't reuse them again. So I couldn't say like PT and SW and RU and QV. Hey, there's my 3 sets. I'm done. Okay, I want you to try to stretch your brain a little bit more and use some different lines. So, what if I said TW? TW down here is going to be parallel to, I could say UV, line UV, sorry. And now I can't use TW or UV. Okay. So my third one, I could say, I don't know, SW is parallel to QV. Can't use them anymore. And there are many other examples I could give, but I'm not. I'm not going to go do and exhaust all the possible options. All right, here's what I want you guys to do as part of your homework, if you will, is see if you can give me 3 sets of skew lines. And can you, again, do it without repeating a line? So I want you guys to do this example on your own. If you want to pause the video real quick and do this example, you certainly can. I just have 2 more slides, real quick slides to do. So you could do the next 2 slides with me, and then when the video is over, go back and do this example. Okay? Now there are many examples here. There's more than 3, but just give me any 3 that you can find without repeating a line. So parallel planes. We talk about parallel lines, but parallel planes, and we kind of talked about this in the last video, are planes that do not intersect. So which planes could you call parallel? Well, you know, like the top and the bottom, the left and the right, the front and the back. But if we wanted to be specific with it, you know, let's say I want to do the left and the right. Well, there's the left plane, if you will. So I need to call it plane, and I need at least 3 letters to name this plane. I'm just going to use all 4, kind of the 4 corners here. Start with P and then go in a clockwise direction. So PSWT is parallel to the right side over here. And I'm going to start with R, plane RQVU. And again, if I go clockwise in this way, in this direction for this plane, I don't have to go clockwise in the same direction at the same point in the other plane. I could go counterclockwise. I could start with V and go counterclockwise. It doesn't really matter. Okay, now that's just one example. I could name the top and the bottom planes or the front and the back planes, but I think you get the idea. The last thing I want to talk about are skew planes. You know, we talk about parallel lines and skew lines. We talk about parallel planes. What about skew planes? Okay, skew planes would have to be planes that do not intersect, but they'd have to be non-coplanar. Okay, so let's talk about the bottom plane here. WVUT. Let's talk about this plane, and let's see if we can discover a skew plane. All right, so which planes would automatically be ruled out? Well, the right side touches the bottom plane, right? It touches it at line UV, so we couldn't talk about the right plane. We couldn't talk about the left plane because it touches it. We couldn't talk about the front plane because it touches the bottom. We couldn't talk about the back plane because it touches the bottom, which leaves us with only the top plane. Only the top side doesn't touch the bottom, but they have to be non-coplanar. Are these 2 planes non-coplanar? Are they? Are they non-coplanar? They are technically coplanar. They share a common plane with each other. So really, and I just threw this out here because inevitably some student asks about skew planes. Skew planes don't exist. I just want to throw that out there just in case you were thinking about it. And that is all for the 3rd video, if you will, section 1-4. I hope you had fun, and we will see you tomorrow in class, and we will work. Adios and goodbye.